You have spent your entire life looking at the moon and seeing stillness, a pale disk that rises, drifts, and sets with such quiet regularity that it almost feels decorative, like something painted onto the sky rather than something alive inside a violent solar system. And I want you to hold that image in your mind for a moment, because what happened on April 6th, 2026 quietly breaks it. 4 astronauts flew behind the moon on a free return trajectory. Not to study impacts, not to run a dedicated observation campaign, but simply to test a spacecraft in deep space. And while they were there, while the sun slipped behind the lunar limb and the surface below them fell into darkness, they watched the moon get hit, not once, not twice, at least 5 times in about an hour. Brief flashes appearing on the dark terrain, like someone striking flint in vacuum. Each one a real collision. Rock meeting rock at speeds so extreme that the distinction between solid and vapor disappears almost instantly. You might be tempted to imagine these as tiny sparks, harmless, almost delicate, but the physics refuses to cooperate with that intuition. Because even a small meteoroid traveling tens of kilometers per second carries enough kinetic energy to release an explosion comparable to tons of TNT, not because the object is large, but because speed in space turns even small masses into violent events. The astronauts weren't scanning for this. They weren't primed to expect it. They were simply looking, and that matters. Because when you see something unexpected in a place you thought you understood, your brain does something subtle. It stops treating the environment as background and starts treating it as active. The moon below them wasn't a postcard anymore. It was a surface being rewritten in real time. What makes this moment so unsettling is not just the flashes themselves, but the comparison that immediately follows. Ground-based monitoring programs detect on the order of a couple dozen visible impacts per year, yet here were 5 in 60 minutes. And you don't need to run the numbers to feel the tension, because your intuition already senses the mismatch. Either this was a statistical coincidence, or the moon is doing far more than we've been able to see. And I find it useful to think about this the way you'd think about standing in a dark field during a meteor shower. Except instead of watching streaks burn up harmlessly in Earth's atmosphere, you're watching them actually hit the ground, one after another, with no air to slow them, no glow trailing across the sky, just sudden flashes at the moment of impact. From that vantage point, distance stops protecting your assumptions. The crew was close, a few thousand kilometers above the surface, with no atmosphere between them and the moon, no scattered light, no shimmering distortion, just vacuum and contrast. And that combination turns faint events into visible ones, like removing fog from a window you didn't realize was cloudy. I want you to imagine how quiet that must have felt. The corona blazing around the black disk of the moon, earthshine faintly illuminating craters, and then a flash, brief and sharp, followed by darkness again. No sound, no plume drifting away, just evidence that something struck and the surface absorbed it without ceremony. The important thing is not that the moon suddenly became dangerous, but that the stillness you've always associated with it was never real in the first place. It was a product of distance, of filtered light, of watching from too far away to notice the small, violent things happening all the time. When you move closer, the illusion dissolves, and the moon stops being a calm companion and starts looking like what it actually is. A world continuously taking hits, indifferent to who might be watching. What the astronauts saw wasn't a dramatic anomaly. It was the ordinary revealed under extraordinary conditions. And once you picture that 5 flashes in an hour on a surface you've always called silent, it becomes hard to look at the moon again without imagining the same quiet bombardment happening right now, beyond the reach of your eyes, whether anyone is there to notice it or not. The strange thing is that nothing about the moon changed during that hour. The impacts were not new. The violence was not unusual. And the physics certainly did not suddenly switch on for the benefit of 4 astronauts drifting behind a black disk in space. What changed was the vantage point, and once you start thinking about that, you realize you have never actually seen the moon the way it truly is. Because every time you look up, you are looking through a filter so familiar, you forget it exists. Between your eyes and the lunar surface sits roughly 100 kilometers of atmosphere, a thick, turbulent layer of moving air that bends light, scatters photons, and quietly erases faint signals long before they reach you. And this matters more than it sounds, because the impacts the crew saw were not blazing explosions lighting up half the surface. They were brief flashes, subtle, easily lost events that only become visible when contrast is perfect and noise is minimal. From Earth, that perfection never happens. The atmosphere ripples constantly, smearing light the same way. Heat waves distort the horizon above asphalt, spreading a sharp point into a blur, diluting brightness until something that was obvious up close becomes indistinguishable from background noise. You've seen this effect yourself without realizing it. Stars twinkle. Planets shimmer. Distant lights seem to dance. And all of that motion is not the object moving, but the air between you and it shifting unpredictably. Now imagine trying to detect a fraction of a second flash on the surface of an object nearly 400,000 kilometers away, while that same shimmering layer is continuously softening the signal, and you begin to understand how much is being lost. Distance compounds the problem in a way that intuition struggles with, because light doesn't just travel, it spreads. And by the time a flash from the moon reaches Earth, it has expanded across an enormous area, its intensity diluted simply by geometry, like the difference between holding a flashlight close to your hand and shining it across a football field. The source hasn't changed, but the brightness you perceive collapses with distance. Combine that dilution with atmospheric scattering, with limited observing windows, with the requirement that the moon's surface be in darkness but still visible. And what you end up with is not a continuous watch, but a narrow, imperfect sampling, a few hours here, a few nights there, all filtered through air that steals the faintest signals. So when ground-based programs report a few dozen detectable impacts per year, what they're really telling you is not how often the moon gets hit, but how often we manage to catch the loudest events that survive a long journey through a noisy system. The crew behind the moon had none of those limitations. No atmosphere, no city light pollution, no shimmering air, and most importantly, they were close enough that faint flashes remained faint but visible instead of vanishing entirely. Think of it like trying to hear whispers in a crowded room, then suddenly stepping outside into silence. The whispers didn't get louder. The noise just disappeared. That is what changed on April 6th. Not the moon, but the background against which it was observed. You might be tempted to assume that telescopes compensate for this, that bigger mirrors and better detectors recover what the atmosphere steals. But there is a limit to what optics can do when the medium itself is unstable, because the atmosphere doesn't just dim light, it reshapes it, scrambling the fine details that distinguish a real flash from random noise. And even with adaptive optics and careful calibration, the faintest events simply dissolve before they can be confidently identified. The result is a quiet bias built into decades of observation, not an error exactly, but a blind spot, where the moon appears calmer than it truly is, because only the most energetic impacts cross the threshold of detectability. The astronauts, by accident rather than design, stepped outside that bias. And the difference is almost philosophical. From Earth, the moon looks like a static object occasionally disturbed. From close range, it looks like a surface constantly absorbing small acts of violence. Once you grasp that, the stillness you've always associated with it begins to feel like an illusion created by distance, the way a faraway storm looks silent, until you're close enough to hear the rain, and what you thought was calm turns out to be motion happening just beyond the limits of your perception. The deeper reason those flashes exist at all is that the moon has no shield, and that absence changes everything in a way that's easy to underestimate if you've only ever lived on Earth, because here you are protected by a system so effective you never notice it. Every day, countless grains of cosmic debris slam into Earth at tens of kilometers per second, yet you don't see them hitting the ground. You see brief streaks of light high in the sky, and you call them shooting stars, something poetic, something harmless, a moment to make a wish. What you are actually watching is the atmosphere doing violence on your behalf, compressing air in front of each particle so violently that the air itself becomes plasma, heating to thousands of degrees, shredding the incoming fragment long before it ever reaches the surface. The rock doesn't gently burn away like a log in a fire. It's torn apart by physics that cares nothing about scale. And in most cases, the particle never survives beyond a few dozen kilometers above your head. The moon has none of that, no thick blanket of gas, no compression heating, no protective burn-up phase, just vacuum from space all the way down to rock. When a particle approaches the moon, it does not slow, it does not glow across the sky. It does not fragment gradually. It simply continues at full cosmic velocity until it meets the surface. And that meeting is not a collision in the everyday sense. It's a conversion of kinetic energy, so abrupt that solid matter behaves like fluid. At 20, 30, even 70 kilometers per second, the time scale of impact shrinks to microseconds, and the material at the contact point doesn't crack or chip. It vaporizes, turning instantly into a superheated plume of gas and molten fragments. A shock wave travels outward through the regolith faster than sound moves through rock, excavating a crater in milliseconds, ejecting debris in ballistic arcs that travel for kilometers because there is no air to slow them, no drag to soften the motion. Just pure Newtonian trajectories played out in silence. The flash the astronauts saw is that moment of vaporization, the brief glow of material heated to tens of thousands of degrees before it expands and cools. And the reason it feels surprising is that your intuition expects impacts to look like objects hitting surfaces, something mechanical, something tangible. But at these speeds, the physics becomes more like an explosion than a collision. A walnut-sized rock can release energy equivalent to tons of TNT simply because velocity dominates everything. And once you accept that, the moon stops feeling like a quiet landscape and starts looking like a target left out in the open. You might picture it as standing in a shooting range where projectiles arrive invisibly from every direction. Some tiny, some larger, all moving too fast to see until they strike. The moon sits in that range permanently, exposed to debris left over from comet trails, asteroid collisions, and the constant dust drifting through interplanetary space. And unlike Earth, nothing filters it. Even microscopic particles hit with enough energy to pit glass, and gradually grind surfaces down over time. And larger ones produce flashes like the ones observed from orbit. The remarkable thing is not that these impacts happen, but that we ever thought they were rare, because once you remove the idea of atmospheric protection, The moon becomes exactly what physics predicts: an airless body continuously absorbing the solar system's leftovers. Every crater you see, from the giant basins visible to the naked eye to the tiny pits covering every grain of regolith, is part of that same process, just recorded over different scales and times. Nothing erases them. Nothing smooths them out. So the surface becomes a layered history of impacts stacked over billions of years, each new strike adding to a record that never fades. When you imagine the flashes again in that context, they stop being isolated events and start looking like the present tense of a story written across the entire moon. A story where silence doesn't mean inactivity, only that the explosions happen without sound, without atmosphere, without warning, leaving behind a world that appears calm only because the violence happens too quickly and too quietly for distance to reveal. If you place the two most quoted numbers side by side, your intuition immediately rebels because one of them feels calm and the other feels impossible. Roughly 20 confirmed lunar impact flashes per year from ground-based monitoring, and 5 or 6 seen in about 1 hour by a crew passing behind the moon. Your first instinct is to multiply, to scale that hourly rate across a year, and conclude that tens of thousands of impacts must occur. But that instinct, while natural, is both wrong and deeply revealing, because the mistake lies in assuming those two measurements describe the same thing. They don't. One is a count of the brightest events visible through a noisy, distant observing system, and the other is a glimpse taken under nearly perfect conditions, closer, darker, cleaner, where the detection threshold drops dramatically. What you are really seeing is not a disagreement in lunar activity, but a disagreement in what our instruments can detect. And once you start thinking in terms of thresholds rather than totals, the whole picture shifts. Imagine standing in a quiet field at night counting lightning bugs, except you're doing it from a hill miles away through fog, and you only count the brightest flashes. Then suddenly you walk into the field itself and discover the air is full of dimmer flickers you never noticed before. The bugs didn't multiply. Your sensitivity changed. The lunar impact environment behaves the same way because the distribution of impactor sizes follows a steep power law. Large objects are rare, smaller ones are vastly more common, and each step down in size increases frequency dramatically. That means the events we detect from Earth are not typical. They are the loudest members of a much larger population. Beneath them lies a cascade of smaller impacts, each producing less light, each more difficult to see from a distance, but collectively dominating the true activity on the surface. The flux models built from crater statistics, dust detectors, and return samples have been suggesting this for decades, indicating that more than a ton of meteoroid material strikes the moon every day, most of it in particles too small to produce visible flashes, yet still carrying hypervelocity energy. When you hear a ton per day, it sounds abstract, like a number that floats without meaning. But picture it as a continuous drizzle of high-speed debris, not a single event, but countless tiny impacts spread across the entire surface, each one microscopic, collectively relentless. This is where intuition breaks, because you naturally focus on the spectacular, the flashes the astronauts saw, the visible explosion. But the real environment is dominated by the invisible majority, the impacts that never produce enough light to be seen from Earth and barely enough to be seen even from orbit. The ground-based detection rate of 20 per year is therefore not a measure of total impacts, but a floor. The minimum number bright enough to survive distance and atmospheric noise. The true count of flash-producing events above a lower threshold could easily reach thousands per year. And below that, the number of smaller impacts climbs exponentially. When the Artemis crew observed several flashes in an hour, they were effectively sampling deeper into that distribution, not because the moon was unusually active, but because their vantage point allowed them to see events normally buried beneath detection limits. This is a subtle but profound shift. The moon did not become busier. Our measurement became more complete. You might be tempted to think this only matters to scientists refining models, but it matters to anyone imagining activity on the surface, because the environment you design for depends on which part of the distribution you believe. If you assume only the brightest impacts matter, the moon looks intermittently violent. If you account for the full cascade, it looks continuously active. The difference is not academic. It's conceptual. The difference between occasional events and constant bombardment, once that idea settles in, the 5 flashes the crew saw stop feeling like anomalies and start feeling like a window. Brief and imperfect, into a process happening at scales. Your intuition was never trained to visualize. The numbers don't just stretch your expectations, they quietly dismantle them, replacing the image of a mostly quiet world with one where activity is defined not by dramatic explosions, but by the overwhelming frequency of things too small to notice. Except when you finally move close enough that the silence begins to flicker. There is an uncomfortable twist hidden inside all of this. Because the place we are most eager to build on the moon, the region repeatedly described as the safest, the most practical, the most promising, is not outside the bombardment at all. It is simply the place where the trade-offs look best. The lunar South Pole has become the focus of nearly every serious long-duration plan, not because it is gentle, but because it offers advantages that are too valuable to ignore. Ridgelines that catch near constant sunlight for power, permanently shadowed craters that trap water ice, thermal conditions more stable than the equator's brutal swings, and geometry that allows continuous communication with orbiting infrastructure. On paper, it looks like the closest thing the moon has to livable real estate. But paper has a way of smoothing out the environment, and the impacts the Artemis crew observed remind you that no latitude escapes the same cosmic rain. At least one flash appeared near the polar region, not statistically decisive, but psychologically difficult to dismiss because it places a visible event directly over the coordinates where humans plan to assemble habitats, landers, power systems, and long-term infrastructure. You can model flux variations with latitude, and indeed some calculations suggest slightly lower rates at the poles for certain particle populations, but slightly lower in a continuously bombarded environment does not transform danger into safety. It merely adjusts how often the same physics plays out. Imagine standing under a roof with fewer leaks than the rest of the building. You might choose that spot, but you wouldn't call it dry. The South Pole is that roof, advantageous, rational, yet still exposed. The moon does not care where we prefer to build, and debris does not select landing sites based on engineering convenience. Particles approach from every direction, guided by orbital mechanics rather than human planning. And when they strike, the distinction between equator and pole collapses into the same fundamental event, hypervelocity energy meeting, exposed surface. The irony is that the very features that make the South Pole attractive, long shadows, crater rims, complex terrain, also complicate our ability to monitor it fully, creating pockets of darkness where small impacts may occur unseen, reinforcing the idea that the calmness of the region is partly observational, not physical. You might think of it like choosing a campsite in a valley sheltered from wind. only to discover that stones still fall from the cliffs above. Not constantly, not catastrophically, but often enough that you begin to notice the ground around you slowly filling with debris. Over short visits, that environment feels manageable. Over years, it becomes something else entirely. The plans for polar habitation stretch far beyond brief landings, envisioning months, then years, then permanent presence, and time is the multiplier that transforms low probability into inevitability. A habitat sitting in one place accumulates exposure, not in dramatic moments, but in quiet increments. Each small impact adding to the history of stress, erosion, and potential failure. The South Pole does not eliminate that arithmetic. It simply offers benefits that outweigh it. That distinction matters because it reframes the decision. We are not choosing a safe region. We are choosing the most useful region within an unsafe environment. The flashes seen near that latitude, even as isolated observations, make the abstraction tangible, reminding you that the ground under future landing pads is part of the same target field as every other part of the moon. When you picture sunlight grazing crater rims and ice locked in shadow, it is tempting to imagine stability, but the physics operating above those landscapes remains indifferent. Particles crossing interplanetary space at enormous speeds, arriving without warning, leaving behind tiny signatures that accumulate whether anyone is watching or not. The South Pole remains the logical place to go. Yet logic does not soften the environment. It simply acknowledges that we are choosing to live where the advantages justify enduring a steady, invisible rain of impacts, a compromise that feels reasonable only until you picture those faint flashes appearing over terrain we plan to call home. Once you stop thinking about the moon as a destination and start thinking about it as a place where people actually live, the scale of the problem shifts from dramatic flashes to something quieter and far more persistent, because the real engineering challenge is not surviving a single large impact. It is surviving the continuous rain of micrometeoroids that never stops. These particles are tiny, often smaller than a grain of sand, sometimes thinner than a human hair, and your intuition wants to dismiss them immediately. But velocity rewrites their significance, because at 20 kilometers per second, even a speck carries enough energy to behave like a microscopic bullet. A habitat on the lunar surface is not just sitting there, it is being sandblasted by the solar system every hour, every day, with no atmosphere to absorb the hits, no magnetic field to deflect them, and no erosion process that gradually smooths the damage away. Studies estimate that a structure with exposed area comparable to the International Space Station could experience tens of thousands of micrometeoroid strikes each year, not catastrophic individually, but relentless in accumulation, each impact carving a tiny crater, generating shock waves in material, weakening coatings, pitting windows, and slowly turning smooth surfaces into something rough and compromised. You might imagine the effect like holding a piece of metal in a stream of sand, except the grains are invisible and moving faster than rifle bullets. And the stream never shuts off. The problem is not that one of these particles destroys the habitat instantly, though that remains possible, but that thousands of them gradually erode the margin of safety until the structure is living on borrowed tolerance. We have already seen this process in low Earth orbit, where spacecraft surfaces return peppered with microscopic impact marks, windows chipped, radiators pitted, handrails scarred, evidence that space is not empty but filled with fast-moving debris. The difference is that those spacecraft orbit within a partially protected environment, and for limited durations, while a lunar habitat would sit exposed in interplanetary space for years, unable to rotate away from risk, unable to retreat, accumulating damage silently. Engineers respond to this with layered shielding, the Whipple shield concept, where an outer bumper breaks incoming particles into a cloud that spreads before reaching the inner wall, reducing penetration risk. It is elegant, effective, and widely used, yet it is not absolute. And when you apply a small failure probability to tens of thousands of impacts over decades, the arithmetic stops feeling comforting, even if nearly all particles are intercepted. The tiny fraction that penetrate becomes statistically inevitable over long time scales, and on the moon, a penetration is not a minor inconvenience. It is a pressure leak in a place where outside is vacuum and inside is life. You can design redundancy, multiple pressure layers, rapid patch kits, monitoring sensors, but each addition increases mass, complexity, and construction difficulty, and the habitat begins to resemble less a building and more a survival system continuously defending itself. This is why many long-term concepts abandon the idea of exposed structures entirely and instead propose burying habitats beneath meters of regolith, using the moon's own pulverized surface as shielding, not because it is elegant, but because it is practical, mass already in place. Thick enough to absorb both micrometeoroids and radiation, the image shifts from gleaming modules sitting on open terrain to something closer to an underground installation, carved into the debris of billions of years of impacts. Using the past violence of the moon as protection against its present, that solution solves one problem and introduces others. Construction complexity, excavation machinery, psychological isolation, but it reflects a deeper realization. Living on the moon is less about building outward and more about hiding from the environment. When you picture a habitat slowly buried under gray dust, you are not looking at an architectural choice. You are looking at a concession to physics, an acknowledgement that survival in this setting means minimizing exposure to a crossfire that never pauses, never announces itself, and never grows tired, leaving any structure above the surface to negotiate with a constant stream of invisible impacts that gradually redefine what durability really means. There is something almost deceptive about how quickly each flash disappears, because the light lasts less than a second. The surface returns to darkness, and if you were not watching carefully, you might convince yourself nothing meaningful happened. Yet the reality is that every one of those brief bursts leaves a permanent mark, a crater, a scatter of ejecta, a tiny rearrangement of the lunar surface that will remain for millions of years. The silence after the flash is not emptiness, it is aftermath. And once you understand that, the moon begins to feel less like a static object and more like a slow-motion record of continuous change written in impacts too brief to notice individually. What Artemis II really altered was not the physics of the moon, because those processes were always there, but the human relationship to them, the shift from knowing something abstractly to witnessing it directly. Before that moment, the lunar bombardment lived in models, in flux curves, in crater statistics, in numbers that sat comfortably in papers. After that moment, it became experiential, something you could imagine seeing with your own eyes, something that felt immediate rather than theoretical. That transition matters in a way that is difficult to quantify, because human decisions rarely respond to equations alone. They respond to images, to moments that collapse distance between concept and reality. When you imagine the astronauts drifting behind the moon, the corona blazing around the rim, earthshine faintly illuminating the terrain, and then a sudden flash, you are not just processing data, you are witnessing a world behaving differently from the quiet companion you grew up with. The moon did not become more dangerous. It simply stopped pretending to be calm. There is a subtle lesson hidden in that, one that extends beyond lunar science, because it reminds you that environments do not change when we notice them. Only our expectations change. The moon has been absorbing debris for billions of years, accumulating a history that never erodes. Every crater layered atop older ones, a surface shaped entirely by impacts. The crew did not reveal a new phenomenon. They revealed continuity, a process that never pauses. Even when no one is there to see it, that continuity is what makes the silence afterward feel different. Because the absence of visible motion no longer implies inactivity, it implies events happening too fast or too faint to register from a distance. Once that idea settles in, you begin to picture the moon not as frozen but as quietly active. A place where change happens in sudden bursts, separated by long stretches of apparent stillness. Like a time lapse unfolding too slowly for casual observation. The psychological shift is subtle but profound. Instead of asking whether the moon is active, you start asking how much of that activity we fail to perceive. Artemis 2 did not provide a complete answer, but it removed the assumption that our previous view was complete. The flashes did not redefine the moon. They redefined our confidence in our own measurements. And that realization carries a kind of humility, because it suggests that even familiar objects can hide dynamics just below the threshold of perception, waiting for a different vantage point to reveal them. The moon remains silent, airless, indifferent. Yet now that silence feels less like calm and more like the quiet between impacts. A pause that only seems permanent until another unseen particle crosses the void and briefly turns darkness into light, leaving behind a mark that endures long after the glow fades.